Yeah, thanks. So before starting, I would like to say this is joint work with Francois, who is still in Paris for a couple of weeks and soon be moving to Singapore. Motivational slide. Why are we interested in mixed quantum classical dynamics? What is it? The motivation comes from different directions, actually. Foundations of physics. Measurement theory involves the coupling between quantum and classical dynamics. Gravity theories involve the coupling of quantum and classical degrees of freedom. Our own motivation here comes from problems in quantum chemistry. Fully quantum simulations are very expensive, so one wants to treat nuclei as classical while leaving electrons as fully quantum, and I would advise attending Bergel's talk for more on this point. In this particular case, we were interested in solvation, so how quantum solid molecules interact with the solvent, which is a classical liquid solvent around it. And there are also motivations coming from spintronics. Problem with quantum classical dynamics is that most models are inconsistent, and they often violate the uncertainty principle, one of the examples of the inconsistency. So this is the project that we are involved in. This is the problem is again studying the solid-solvent interaction, and this is a project involving Frankfurt, Singapore, Toronto, as well as Surrey. The problem in devising this kind of models is that mean field factorizations are insufficient, so you cannot really do things easy because you really need to capture correlation effects. So what are the consistency requirements for these type of models? The classical subsystem must have a positive probability density on phase space. The quantum subsystem must have a positive semi-definite density operator. In the absence of a coupling potential, where the Hamiltonian is a direct sum Hamiltonian, the mixed dynamics must reduce to uncoupled quantum and classical flows. We also want the equations to be equivariant with respect to classical canonical transformations and quantum unitary transformations. This is for ensuring the correct balance laws. And also, and this is tricky, when the coupling is not zero, then the norm squared of the density matrix, which is called quantum purity, must have non-trivial evolution in times. So as we are aware, the only Hamiltonian model possessing these, all of these consistency properties is the so-called Ehrenfest model. This is nomenclature coming from chemistry. So we have a probability density that satisfies an advection equation. We have a local density matrix. So this is a density matrix depending on Q's and P's. This is advected, but also undergoes its own unitary evolution. Some notation for the vector field that appears in the advection terms, and this is how we compute the full quantum density matrix of the quantum system. The problem with this model is that this is known to fail in reproducing accurate results. So there is a problem with accuracy here. Okay, so it's too elementary, it's too simple. We need to go beyond this. There are two common approaches that one can follow to devise these mixed quantum classical models. The first one is, okay, let's try to write quantum systems in terms of Liouville-like probability densities. We know how that works. We can look at Wigner densities. It's been done in many contexts. The problem with Wigner is that its evolution involves the Moyal brackets, and that are very, very complicated to work with. There is another proposal, which is, okay, let's instead write classical mechanics in terms of Schrödinger-like wave functions. And this actually goes back to work by Koopman in 1931. But the proposal in quantum classical dynamics comes from an old paper by Sudarshan in 1976, and I will say more about this. The trick about Koopman wave functions is that they undergo linear unitary dynamics, so they are really mimicking the quantum evolution. So this is how things work. So if we have an L2 function undergoing this equation where H is the classical Hamiltonian and this is the Poisson bracket, then chi mod squared satisfies the classical Liouville equation. All right? So the main observation is that this operator here, which generates the motion and is known as the Liouvillean, this is a self-adjoint operator. So this Koopman von Neumann equation really does give you a unitary evolution, linear unitary evolution in a space of square integrable functions. So Sudarshan extended this type of systems to include quantum degrees of freedom. However, things turned out to work differently from what he expected initially. And what we wanted to do was to rescue somehow these ideas. Right, so this is Sudarshan in Kiev. This is in company of Nikolai Bogolyubov. And this is the title of his paper. And there are two main ideas that are contained in this paper. The main idea, which is the most intuitive and simple idea, is okay, so if classical mechanics is unitary and so is quantum mechanics, let's take the tensor product evolution. And yes, so that is very intuitive. However, you have to work harder to figure out what kind of infinitesimal generator you need to write these equations. And then there was this mysterious idea coming from physics. So we need to make classical phases unobservable, whatever that means. Okay? Another way of saying is that, yeah, okay, we don't measure Hamilton-Jacobi functions. So the classical phases are in the game, but somehow we have to mod them out in a certain way. And that took us a long time to figure out how to do it. As I said, there were difficulties in the first implementation of these ideas that attracted a lot of criticism. So we rescued these ideas, and in order to do this, we used the PhD work of Leon van Hove on prequantization. We blended it with the Koopman von Neumann equation. And then eventually we used gauge principles to make these phases unobservable. So the phases here are treated as a gauge freedom. So this is a PQ dot minus H type of action principle. And I am going to explain what everything means here as much as I can. So this is the elementary action, and this is the total energy Hamiltonian function now. There is an intuitive term, which is simply the average of the Hamiltonian, but then there is a nasty term, which I'm going to tell you more about. So the title refers to Lagrangian trajectories. Where are the Lagrangian trajectories here? Well, I mean, this action principle is fully Eulerian, but of course, by Euler-Poincare reduction, we know that if we have a vector field here, we also have Lagrangian paths that obey this type of equation here. Analogously, the density is advected along the paths. And so this is how Lagrangian and Eulerian variables are related. So this stuff somehow comes from the first term. We also know that there is a unitary, quantum unitary propagator parameterized by Q's and P's, here the classical Q's and P's, in such a way that this local density matrix is transported by the diffeomorphisms, the diffeomorphic paths, but also acted on by the unitary group in such a way that the resulting orbits are orbits of a semi-Dirac product action, the semi-Dirac product being the diffeomorphisms of phase space with mappings into the unitary group. Right, so this term here corresponds to PQ dot in Eulerian coordinates, so this is the classical PQ dot, and this other term here corresponds to psi dot in the Schrödinger Lagrangian, which is standard in quantum mechanics. Then, as I said, there is this piece, this average in the total energy, and then there is this extra term, which is what everybody in chemistry is looking for. We call it the back reaction term. It's an extra term that turns out to involve, quite surprisingly, a non-abelian gauge potential also appearing in a kind of far topic, which is known as spin-orbit coupling. This was we had no idea that this was going on. We found this non-abelian gauge potential, and then we realized by chance that yes, I mean, it's also there in spin-orbit coupling. So we intend to pursue this direction later, actually. Right, so what we obtain is a nonlinear quantum classical evolution PDE, which modifies, so if this H is the standard Hamiltonian, this is the same as the Ehrenfest model that I showed you. But now, this H here possesses H-bar corrections coming from the back reaction term. All right, so now, this back reaction term is giving you one of the nastiest things you have ever seen, because it involves lots of extra nasty terms, which if you are an analyst, you just run out of the room. Now, despite the intimidating look, what we observed is that these PDEs here involve no gradients of order bigger than 2, which was kind of encouraging. As I explained, dropping the H-bar terms also yields the Ehrenfest model. Interestingly enough, there is also a quantum classical Poincare invariant, which I don't show it here, but it actually leads to a quantum classical definition of entropy, extending or incorporating both the Gibbs entropy from classical dynamics as well as the von Neumann entropy from quantum mechanics. As it stands, I said again, the system is hardly tractable, so we need closures. By closures, one can devise closures of different kinds. The first thing we did was devise closures for numerics, like trajectory models. And indeed, we devised a method which we called Koopman. This is a particle method to somehow see what this model gives you. And again, I would address you to the talk of Paul Bergold later today. But here, what I'm interested in is fluid closures. Okay, so instead of having a phase space formulation, which can be computationally pricey, let's see if we can devise a fluid closure on the configuration space. Right, so in order to do that, instead of operating on the equations of motion, which would be completely hopeless, we try to benefit from our knowledge of the structure underlying the action principle. This is what we are going to do. We start from the phase space, the action principle on phase space, and then we try to apply subsequent approximations coming from the geometry to each of those terms. So the first thing that we want to do is look at this guy. This is, like I said, this is another version of PQ dot. This is on phase space. How do we actually take, for example, this vector field down to the configuration space? We can actually use a group inclusion or a group restriction by resorting to cotangent lifts. right? So we have phase-space diffeomorphisms, but we know that they contain a subgroup called cotangent lifts. And so given diffeomorphisms on the configuration space, we can lift it to phase space, and this is going to be our group of interest here. So right, so this is how our X here is going to be written from now on. Same thing, actually even more simply, we drop the P dependence on the unitary propagators in such a way that the infinitesimal generator is now entirely defined on the configuration space. Right, so this amounts to taking care of these two guys, and so we have the elementary action here produces the usual m dot u coming from the phase space Lagrangian in fluid dynamics, as well as the analog of this term, but now on the configuration space, where now this rho plays the role of P. Right, so now what about the Hamiltonian? The quantum back reaction is really the main problem here. This takes us beyond the Ehrenfest average and is produced by inhomogeneities in the quantum state variable P, which is this local density matrix. Right, so in order to keep things simple, we start by taking a cold fluid ansatz. We will relax these ansatz later on, but for the moment, this is what we do. And then we also write the Hamiltonian, the quantum classical Hamiltonian as classical kinetic energy plus whatever depends only on the classical position coordinates. So this is how our Hamiltonian becomes. Like, this is the first piece of the Hamiltonian, and we'll restore pressure later. And now we have to take care of the back reaction term. Right, so if we now rearrange things a little bit, so we replace this Hamiltonian in here, we get this guy, divergence of the commutator of rho with kappa, where kappa is this nasty guy here. Problem is, we need to find the closure for this kappa in terms of these other variables that we have on the configuration space. So in order to find this closure, we asked for two simple properties to be satisfied. Just for the sake of simplicity, we want kappa to be linear in the gradient of rho. And also, we want no higher order gradients coming from this guy. And these are properties that are also appearing in the original model. So we want to mimic the structure here. So in the simplest, so this means that my kappa must be written in this way. So I have a one form wedged with a differential of my rho. And in the simplest case, my one form is written in this way. So minus C differential of B. So if I now do that, surprise, surprise, I get an Ambu bracket. Okay, so this was again one of the surprises in this business. We were not really looking for it. It just popped up, but out of these assumptions. So interestingly enough, we go from a canonical PQ bracket to another bracket here, which is the Ambu bracket. So if we now restore the internal energy, this is how our Lagrangian becomes. This is the last two terms identify the total energy. So then, same problem as in the previous talk, we need to write the variations. And it turns out that importantly, this B variable needs to be Lie transported in order to ensure momentum balance. And so in conclusion, this is how the variations arise. The equations are again quite a nightmare, but there is something interesting going on here. Because if we now compare this nightmare of equations with the equations of quantum hydrodynamics, which was lectured on by Mauro early on, what we actually see is that we change nasty second-order gradients appearing in the quantum terms with first-order gradients only. So no matter how complicated, and it is very complicated, this model is, it only contains first-order gradients. Right, so, and this is the comment that I wanted to make here. So the model is Hamiltonian. Interestingly enough, the Poisson bracket is the same bracket as it appears in complex fluid dynamics. And interestingly enough, now the Nambu bracket is part of the Hamiltonian functional. It's not that this is Nambu dynamics. This is not Nambu dynamics. This is simply a back reaction term that appears in the Hamiltonian. All right, so it's a fluid system. We know what we are doing here. We know this bracket. We have seen it several times. So there are infinite families of Casimirs, and people who come from plasma physics may be interested in knowing that there is a cross-helicity appearing here. Right, so we actually specialize this model to a very simple type of systems, which is called pure dephasing systems. The Hamiltonian is written in this way. What happens for the Ehrenfest model, and we know that this model is very simple, is that in this case, the classical flow decouples. So this is how bad you see that the Ehrenfest model is. The Ehrenfest model entirely collapses for this type of systems. And, well, this doesn't happen for our model because since this equation is non-trivial, then we avoid the collapse of this model in this very simple case of pure dephasing dynamics. Then the crucial question, and this is the question that closes this talk, is how, okay, so all fine, but how do we initialize this back reaction field B? Well, one can use the energy Casimir method to provide equilibrium profiles that isolate possible equilibrium profiles of B. But actually, even more simply, we can go to the two-dimensional case in which B just disappears because it's expressed in terms, it's a linear expression involving just a constant. And so we can actually start with 2D configurations. Right, so these are some next directions in mixed quantum classical dynamics that at least I want to pursue. And I will leave it there. Thank you.
Thank you very much. Are there some questions?
I have a question to the fluid closure. More in general, like if you have a phase space formulation, a phase space Lagrangian, and then you, if I understood correctly, you impose that the one form is a cotangent lift, right? Arises from a cotangent lift, right? So do you have an idea what physically this means, this closure?
So one thing I should add is that I wrote it in the slides, but I didn't mention it. That's not the only thing we do. We also take moments, of course. So this closure, this restriction to cotangent lifts allows for the moments to be closed. So physically, what it means is that this is, this is, I don't know, it depends on what we mean by physically here.
For example, in collisional closures, you know,
collisions.
It's a Maxwellian, right? But in your case, it's something else. So what is the assumption that you do by doing this?
So if we can use a Maxwellian in the total energy. We can use that, and in which case we can recover the internal energy. But then we still need to take, so these are different things. So there is a geometric part and there is a physics part. The geometric part comes from the elementary action, which is the PQ dot part. So that's purely a geometric term, and that's where we use this cotangent lift stuff. And we need to do that, right? But then there is physics, and the physics is in the Hamiltonian.
But there might be other ways instead of the cotangent lift, right? So this is a one-shot.
Well, the other way is you can operate on the equations and take moments of the equations, but then good luck with that. I mean, the equations are nasty enough to discourage pretty much anybody. Yeah, thank you.
More questions? If not, we can thank Cesare again.